Hey everyone, and welcome to the 2-day workshop. I will be calling on the host, Lukumon, to give a brief introduction about himself and also tell us what we are going to be learning today. And Lukumon, can you unmute yourself, please?
Hi everyone. Sorry, can you hear me?
Yes, I can hear you.
Okay, thank you. So hi everyone. Thank you for having me. My name is Lukman Latif. So I have a master's degree in geospatial technologies, and I'm using Earth observation, like satellite images and some other data to carry out like some tasks such as like land cover, flood mapping, and the like. And I also train people on how to use like geospatial software, including QGIS, and I enjoy like sharing knowledge and also like learning from others. So today we're going to be looking at like the first part of a 2-day webinar series, which we are going to try to understand the fundamental concept of satellite image analysis before we now proceed to the practical aspect tomorrow. So maybe we can wait for a few minutes, then I will proceed to share my slide and properly commence the presentation. Sorry, please, can you confirm if you can see my screen?
Yes, we can see your screen.
Okay, thank you. So I will proceed with the presentation. So today we'll be looking at the fundamentals of satellite image analysis to set the background for the practical class that we're going to have tomorrow. So today's talk will center on trying to understand satellite system and how they observe or represent features on the Earth surface in form of image. We also look at the reflectance properties of several or most common features on the Earth surface, and we look at several techniques that we can use to interpret or identify features on an image. And finally, we're going to look at classification methods and approach that are available that we can explore to classify our image. So we begin by looking at satellites and features on the Earth surface. How does satellites represent feature on Earth surface? So I've made a simple illustration because I understand we are coming from several backgrounds, which might not be core remote sensing background. So I will demonstrate the process in which images is being formed or acquired by satellites. So we have a source of energy. In most cases, is the natural source of energy, which is from the sun in the sky. So this sun sends illumination in form of electromagnetic radiation. So this energy or radiation passes through several layers of the atmosphere. Then it gets to the Earth's surface. So it shines or reflects its features on the Earth's surface. So part of this energy that it's or that shines on the feature is being reflected back to the atmosphere. So in this process, we have a sensor, which could be our smartphone camera. It could be a photographic camera, and it could be a satellite sensor. And of course, it could be our own eyes. So we capture the reflected energy from the feature or from the object, and this is being converted to an image. So basically, these are like the 5 major components that form the way an image is being acquired. So you have the energy source, most time from the sun, the natural source. It passes through the atmosphere. It shines on an object. Part of the energy is being reflected back to the atmosphere. And the sensor capture the reflected energy, which is being converted to a digital image. So this we said like the background for our discussion. Then we proceed further. So when we talk about image, we see image most time in color, but image are not only color. So image are made up of like pixel, which are reflected energy or digital number. So for example, looking at this image sample, you can zoom in to a portion of the image. So you begin to see some kind of fuzzy or irregular or unclear boundary. So when you zoom in further, you see some uniform grid, which are called pixel. So each of these pixels contain a unique number, which is the amount of energy that was reflected by the feature. This energy, most time in remote sensing, are being converted to reflectance value. So each of these pixels have their own value. So if you click on this, for example, on the software, you get the value of the pixel here, which could be several parts of the electromagnetic spectrum, which I'm going to elaborate in the subsequent slide. So I talk about energy from the sun passing through the atmosphere and hitting the object. But this energy are in several forms. So you have this spectrum, which is popular spectrum, called electromagnetic spectrum. So the major thing that distinguish this energy is the wavelength. So here on the left, you have the energy with a low or lower wavelength. then the wavelength increase towards the right. So in remote sensing, so the wavelength affects how far a energy from the sun can travel through the space to reach the Earth's surface. Because in the atmosphere, we have some gas molecules, some particles, the energy from the sun to reach the Earth's surface. But the wavelength of the energy has a very great impact on how far they can penetrate the atmosphere to get to the Earth's surface. That is why most time in remote sensing, we use the visible, the infrared, and the microwave because they have relatively high wavelengths and they can penetrate the atmosphere or the particles and get to the Earth's surface. And remember, we are focusing on reflected energy. So we can only have energy being reflected if the energy passes through the atmosphere and able to get to the Earth's surface. So most time we perceive objects in visible. So our eyes is a sensor and we have like a photoreceptor that is sensible to the blue, green, and red region. So that's why they call this part visible part. But there are some other portion in which our eyes as human cannot like see, but they are useful for several interpretation of feature on the Earth surface. So part of it like is the infrared and the microwave, which are very important in remote sensing. And we're going to see their application and how several features appear in this different wavelength portion. So majorly in remote sensing, so we use like the visible, infrared, thermal, and microwave, and the wavelength increases. So I talk about using visible, infrared, microwave, and thermal in remote sensing because they can penetrate most of the gas or the particle in the atmosphere and get to the Earth's surface. So this also is being used by manufacturer of sensor to design their sensor so that they know the kind of channel or bands they're going to put in the sensor. So most time when you see a satellite, be it Sentinel, Landsat, Planetscope, even if a drone, if it has 3 bands, we have the blue, green, and red. Then for sensor, like a large sensor, like satellite sensor, they have the infrared and the thermal. That's because we are very sure that we'll be able to get reflected energy from this part of the spectrum. And this is very important. So you see like most of the sensor here, like Sentinel-2, most of the bands are in the visible and the infrared. So it's similar thing for the Landsat. So there are two, I'll focus mostly, or I began my presentation by talking about the energy from the sun. But this is just like to make it very simple for us to comprehend. So we have two different types. So the first one is the passive sensing system, which I've discussed earlier. You have the sun, it sends energy to the Earth's surface. The energy is being reflected back to the atmosphere, which is captured by the sensor. So that's the passive system. The source of energy is from the sun, which is a natural source. Just like you are outside in a very sunny weather, which is very clear. So you can use your phone camera to capture an image without using your flashlight. So in active system, the sensor or the satellite itself, it sends microwave radiation to the Earth surface, which is being reflected back by the feature on the Earth's surface to the sensor. So take this, for example, like you are in a dark room where there is no light, there is no illumination. So you can use the flashlight of your phone to take a picture. But for the remaining part of this discussion, we're going to focus on this passive system. So we talk about radiation, but like I mentioned, the radiation passes through several layers of the atmosphere, and there are several processes that happen. So once the energy is coming from the sun, there is clouds and there are gas molecules, there are particles in the atmosphere. So depending on the wavelength, like I mentioned earlier, so parts of the wavelength can be scattered if the gas molecule is much. So it can be scattered in the atmosphere and this particle prevents the radiation or the energy from getting to the Earth's surface. But in most cases, like the visible, infrared, and microwave parts, so they get to the Earth's surface. So when the radiation gets to the feature on the Earth's surface, so three major things can happen. So the first one is the feature can absorb all the radiation, just like it's inhale all the radiation. The second thing that can happen is like the radiation can go further. For example, if you have a very tiny feature, like a very tiny leaf, the radiation can penetrate through the leaf and also go further to hit another feature and the Earth surface. So this is called transmission. Or the most popular or the most common case is like the radiation bounced back or reflected to the atmosphere. And again, in remote sensing, what we are most concerned about or in satellite image is the reflected energy from the feature. So just to make it very clear again, you have the sun, it illuminates or sends radiation to the Earth's surface. It passes through the atmosphere. It hits the feature on the Earth's surface. The part of the energy is being reflected back to the sensor. The sensor now sends it or transmits the signal to the ground station. Then it's being processed to images that we download, like Sentinel, Landsat, PlanetScope. Then we apply the image for our analysis. So these are like the summary of how the image is being formed. So you could be wondering, like I am talking about energy being reflected, then how do we differentiate feature in an image? Like how are we able to see building different from vegetation, water, different from other features? So we have what we call unique signature of major features on the Earth's surface. So these major features are the water, vegetation, soil, or built up. So soil and built up can be put in the same category. So the way they appear depends on the reflectance, wavelength, and also the amount of energy, as well as the roughness of the surface, which I'm going to elaborate. So this is like a standard or unique properties of this feature. So water, for example, if water is very clear and the sediment or the bottom of the water is clear, so it has a very low reflectance. So the amount of energy that is being reflected by water is a bit low compared to other features. So water mostly reflects the blue portion of the electromagnetic radiation and absorb the green and the red part of the radiation. And as the wavelength increases, like from infrared upward, so water doesn't reflect this wavelength, so it absorbs the wavelength. And when a feature absorbs the radiation, so it appears dark in an image. So vegetation, on the other hand, like it reflects most green in the visible part. So visible is like the blue, green, and red, which is like a range of 0.4 to 0.7. So most time it reflects the green, it absorbs the blue and the red. So that's why vegetation most time it appears green. So the types of radiation that is being reflected by an object or a feature will determine the color that we see with our eyes. But in the infrared, you can see a very skyrocketed amount of reflectance by the infrared, which in the infrared portion by the vegetation, which mostly depends on the leaf pigment. But mostly, if a vegetation is very heavy, so it's going to appear or reflect a lot of infrared radiation. So here, you see some low points, which are what they call water absorption bands. So this depends, which I will explain further in the subsequent slide. So this depends on the water content in the vegetation. So soil or built up has a very kind of simple or straightforward reflectance. So it has like an increasing reflectance from the visible to the infrared. So this curve is very important in interpreting or identifying features in an image. So soil or B-top has a higher reflectance in the visible than vegetation or the water. So I've talked about like the property of each of these three major features. But like I mentioned, the roughness of the surface also affects the way the energy or the feature will appear. So we have what we call a specular or diffuse reflection. So in specular, you have a very smooth surface like a road or a calm water body. So when the energy from the sun or radiation hits the surface, a smooth surface, so the energy is being reflected like in a single or one direction. So the impact of this is that it limits the amount of energy that a sensor can capture. Just imagine like you have a net and you want to catch a ball. So if they throw a single ball to you, you might miss the ball. Or if they throw, let's say 20 balls to you, there's a chance that you can catch 5 out of the 20 balls. So that's the difference between specular and diffuse. So diffuse is like a regular surface, and when the radiation comes and hits the surface, so the radiation is being reflected back in several directions, and the sensor has like the chance of capturing more amount of reflectance. So I will now look into each of these three features in details to see what can actually also affect their reflectance. So the thickness of the leaf is a very important factor that can affect the reflectance of vegetation. So if you see this kind of trees or vegetation, so they have like open space and a very tiny leaves. So this, if the energy coming from the sun hits this kind of leaves or vegetation, so there's a high chance that they will be transmitted further, and just like a small amount of energy will be reflected back to the atmosphere for the sensor to capture. But in the case of very broad and dense leaf, so once the radiation hits this leaf, it's going to transmit a large amount of energy back to the sensor, which is going to represent clearly an healthy vegetation. So another point that could also affect the way vegetation appear in an image is like the growing stage or the health of the vegetation. So here you can see a leaf looking brown, which show like a poor earth. But here, this is looking very green. So this is going to have more or high reflectance value, especially in the green and the infrared, because it's a very heavy vegetation compared to this like a brown leaf. So another point is like the moisture or the water content in a leaf. So we know that water has no or very low reflection in the infrared, so which makes it appear black. So we know like vegetation has high reflectance in the infrared. So if there is a water in a vegetation, it will tend to drag the reflectance amount down, like it will make the reflectance to be very low. So these are some factors that affect reflectance of vegetation in an image. So talking about water, so water also like is affected by what I explained earlier, the roughness of the surface. So here you see like a smooth surface, which is going to result in a specular reflection, and you have like a kind of wave on the water, which might result like to diffuse reflection, and you have more reflection. Although both of them are going to reflect blue, but the amount of energy that is going to be reflected will be higher for a rough surface compared to a smooth surface. So if you are familiar with synthetic aperture radar, sir, so if you see a smooth water surface, so it will appear very dark in a radar image because the amount of energy or microwave energy that is being reflected back is very low because of the surface. So another important point is like the depth of the water and the suspended particle or sediment. So water, the bottom of the water sometimes contains maybe some turbid sediments or some phytoplankton that could influence the way or the amount of energy that a water can reflect back to the sensor. For example, if you have like some plant elements beneath the water, so this plant element, we know that vegetation reflects green, so they can reflect green and influence the water to appear like green instead of blue. Normally, a clean water, like if the depth or bottom of the water is clean, we expect the water to reflect blue radiation and the water will appear blue. But in a case where you have some plant elements at the bottom of the water, so they can reflect green and influence the color of the water. So when you have some soil particle or some dirt beneath the water, so they can also influence the color or the reflection of the water. So talking about the soil, similar thing applies to the soil. So the texture of the soil, maybe rough or smooth surface, the moisture content. So if there is water in the soil, so it can affect the reflectance of the soil, especially in the infrared portion, because water doesn't reflect in the infrared. So before we go deep into the image analysis part, so I would like us to understand the impact of resolution on the image. So we have 4 major types of resolution: the spatial, spectral, radiometric, and the temporal resolution, which I'm going to elaborate further. So here we are showing the same portion of the Earth surface in an image, but you can clearly see the features in this first part. But as the pixel size, like spatial resolution in simple term, can be called like pixel size, just to put it in a simple way. But as the pixel size increase, you see that the features are becoming blur, so it's difficult to identify the feature. So in 10-meter pixel size, it's even difficult to see what are in this image, unless because we have already seen it in high resolution format. So what that means is that, for example, let's say this is 10-meter pixel size. So this means that the minimum size of feature that can be represented here is 10 meter. But in the case where the resolution is about 50 centimeter, so this means that the minimum size of feature that can be represented in a single pixel is 50 centimeter. And this enables us to see features in a very fine details and distinguish the feature. So a major important of this is that in remote sensing or satellite image analysis, most time we deal with image on pixel level. So we are trying to identify what is in each pixel, and each pixel, like I showed at the beginning, has its own reflectance value. So in a case where a single pixel contains almost 4 features, like the grass, the building, and maybe some other grand features. So the reflectance from this pixel will contain several features, and it might be difficult for the model to properly identify what kind of feature is in this pixel. So that's what they call mixed pixel. So another thing is the spectral resolution, which in simple term again can be called the number of bands. I show us the spectrum, and we have the visible blue, green, red. We have the infrared, we have the microwave, and the thermal. But not all sensors have all these spectral channel or spectral band. So in most cases, the more the spectral band, the better the image, especially if you are applying it to several applications like vegetation analysis and the like. For example, most drones have the RGB band, whereas most of them don't have like the microwave, the infrared band. So if you look at this Pleiades image, it's a very high resolution image. It has a spatial resolution of like 2 meters, but it has only just 4 bands. But when you look at Sentinel-2, although it's a medium resolution image, it has a pixel size of 10 meters, but it has a lot of spectral bands. And this will be very helpful to distinguish features because, like I've showed in the curve, each feature behave differently in different parts of the spectrum. So radiometric resolution is just like how well can the sensor distinguish different level of brightness, and it's measured like in bits and 2 raised to the power of the bits. So temporal resolution is just like how often does a satellite revisit a place. Like, for example, now, if you look at this calendar of satellite acquisition over the same study area. So let's say you have an image on the 4th of March. So before you have the next image, it's on the 9th of March. So that is like 5 days interval for the same place. So that's the temporal resolution of this particular sensor, which is 5 days temporal resolution, which is like Sentinel-1, A and B. So now we'll go properly to see how we can identify features in the image after we have understood how an image is formed and how different features react or respond to several parts of the electromagnetic spectrum. So image interpretation is basically like identifying feature or targets on an image, which depends on the properties, like reflectance properties of the target, like we saw for building, water, and vegetation. So we have what we call the visual element, which we can use our own eye to see and identify the features. Also, it's helpful sometimes to have like experts, especially domain experts. For example, if you are looking for mineral or like geologic faults in an image, so you want a expert in geology with knowledge of remote sensing to work on that. So I'll be using like this image to illustrate the spectral curve and how we can apply that to identify these 4 features. So remember, I mentioned about spectral channel band. So there are several bands, like I mentioned, the visible part, blue, green, red, the infrared part, the microwave, and the like. So we're going to look at this part one after the other and see how these features behave or respond to this radiation. So starting from the blue band, so we can see some bright, these 2 features are very bright. So they have, the brightness is just like the intensity of the reflectance, how much energy is being reflected in the blue portion of the spectrum. So these 2 features appear very bright, so which point to possibility of being the soil or built up. So this is the visible part. So this is dark, and this is also dark, but their level of darkness is different. So maybe for now, let's assume we can still not distinguish between these 2 features because both water and vegetation has lower reflection compared to soil. So let's check the green portion of the spectrum and see how they behave. So we can't actually see much difference between them, between like how the features appear here and how they appear in the blue band. So let's check the red portion. So you see that the bit up, they become like brighter compared to maybe how they appear in the blue band, because like the reflection of the soil or bit up is increasing, whereas the water is becoming darker, although you might not see very clearly depending on my screen resolution. But we can see the bit up are very like we can distinguish the bit up compared to the this feature and this other feature. And when we check the infrared band, and that's the reason why it's good to look beyond the visible parts which our eyes can interpret and look at the infrared. So the infrared gives a very different look of the feature. So here, the the object here, which is the water, it became so dark because there is no reflectance of water in the infrared. So it absorbs all the energy in the infrared and it will appear dark. So you see like this feature here, which is by now you should know is vegetation. It appears bright compared to how it appears in the blue, green, or red, because vegetation has a very high reflectance in the infrared part. And you can see this stadium and the building here. So it appears like the reflection decreased because the surrounding vegetation has more reflectance in the infrared compared to the building. So that's why it appeared like the reflectance or the intensity of the radiation for the built-up decrease. So this is just like to illustrate to us how we can use this spectral signature curve to interpret satellite image. So we can now combine the blue, green, and red and see in human eye how this object appear in colored form. So here you see the stadium appearing bright, see the vegetation in green, then you see the building here and the water in like a blue color. So by now, so what do we use to identify this as a stadium? We see a very bright color in the blue band. So we see like a shape that resemble like a stadium. Then we see like some space within the oval shape, which indicates based on our knowledge of how a stadium look like. This indicates the pattern or appearance of a stadium. So for the vegetation, so we saw like a very dark color in the blue band because vegetation absorbs the blue radiation. So it doesn't have a uniform shape. Then it has some kind of rough texture. So you can see the texture here appear rough compared to other features in the surroundings. So the other bit up, so we saw it appears very bright in the blue band, which is the property of soil or bit up. So it has like a rectangular shape, which points to a building or a structure. So for the water, it appears very dark and also like it's very wide, like you don't see the end or the start of it. It occupies a lot of space and it has a very smooth surface. And these are properties of of water body and how it responds to reflectance. So here we have used like the color or the reflectance property, the shape, as well as the texture to try to identify this feature. But there is more than these properties that we can use to identify features in an image, which we are going to see further. So just to remind us again, like what I showed at the beginning. So now we know we have several components or several parts of the spectrum. So here it's like a building. When you check the reflectance of the blue, green, red, and the infrared, so you can check their value and see how they vary for a building roof, which is similar to what we checked earlier. So we check like several individual components or parts of the spectrum. Then later we check the red, green, blue combined together, the RGB natural color visualization. But you might ask, why do we need to use like more than one spectral band to interpret an image? So here you can see these are football field and they all appear green to our eyes using the combination of blue, green, and red, like 3 bands combined together. So also, if you look at a medium resolution, so you can see the field in red, blue, and green, they still appear, the football pitch still appear to have like green color. But here you see some kind of change in color when we use the infrared to see the reflectance of the vegetation. So this RGB, like the part where you set the infrared, is the red channel of the computer. The computer accommodates just 3 bands to view an image. So when you set the infrared band to the red channel of a computer or a software, so the infrared will appear very high, will appear red if the vegetation reflectance is very high. So that's why here you see a red color for this stadium, but this appear like a kind of blue color. So this helps us to distinguish that this could be a football pitch, but it's not, or it might not be a natural vegetation. So it could be like a synthetic grass pitch. And this is important of looking above or beyond the visible and using information in other parts like the infrared or the microwave. So we now take the visual elements and see how we can use that to distinguish features on the X or on the image. So tone, as we have seen, is the most important factor to identify feature in an image. So this is like the intensity level or the brightness level of a feature or the reflected energy. How bright is the energy, or how high is the amount of energy that is being reflected. So even here in the blue band, you can see the water is dark, but you can see some very bright objects in the water. So this is showing us like these are some kind of ship or vessel, and they have different reflectance property compared to the water. So that's why they appear very bright. And as we have seen, buildings or built up, they have high reflectance in the blue band compared to vegetation or water bodies. So they appear very bright compared to the surrounding features. So another important point or factor is the variation in the tone or the brightness in an image. So both of these are grass or green area, but these have like some kind of rough texture and it's clustered together. So which gives us the impression of a forest or trees, while this shows like just like grasses. So shape is also an important factor that we can use to distinguish elements. So here, even without seeing the colored image, so we can see these are farmland, and these are like irrigation, circular irrigation farmland. And also we can see in the colored image. Also, the size of an object is very important. So you can have several built up, but how they built up, are they residential building? Are they manufacturing industry? So here you can see the size of the buildings and also the pattern of our arrangement. So compared to the size of the buildings here and the pattern or the arrangement of the buildings. So you can use that to distinguish them or categorize them into several purposes. Yeah, this is similar to what I showed earlier. So you can use like the pattern or arrangement to classify features, especially if you have the same features and you want to categorize them. So here you can see the buildings are clustered together. They don't have uniform pattern, different roof type. So, but here you see the buildings are built in a very spaced way. They have like kind of uniform space. They have uniform roof and the like. So you can use this to categorize them into different kind of environments. So another thing is like the context or the association between the features. So here you can see some rough textured feature which signify to trees or vegetation. But as well, you can see some bright features which are buildings and the like. So you can call this a forest. So you put it into proper context or perspective, and this should be a park in an urban area. So another point is like you see a linear feature, which should indicate a road, but suddenly you begin to see like some shadow. And what could make a shadow to appear on a road? So the most likely thing is like the road is elevated, which could mean like it's kind of like a bridge at that particular place. So this kind of information help us to identify or distinguish features in an image. So this is just like a simple task where we should be able to like identify them if somebody wants to attempt it. So you can put it in the chat box. So if you can identify the first feature, the second one, and the third feature. So this should be very simple for us to identify. I will pause for a minute to check the chat box. Yeah, thank you for the contribution, Michael. Yeah, thank you, Uche. That's very correct. So thank you all for contributing. So the first one is like a park, because you can see like some kind of built up around the area, although this is kind of like subjective. So this is a runway, like Uche got it right, because you can see some kind of aircraft along the way. Also, you can see like the road, so to say, it terminated at this point. So this gives us like the impression like this is an airport runway. So it's not just an ordinary road. And the second one is very simple to identify. So these are just like buildings. Thank you for the contributions. So now we are going to the final part where we're going to see the methods or approach that we can use to classify images. We can use to classify images and identify features on an image. So classification in simple terms is that we are trying to group objects based on similar properties or attributes. So these are animals or ruminant animals. But how can we know like this is a giraffe, this is a goat, this is cow? So they have several patterns, like different on type. They have different pattern of their skin. They have the length of their neck and so on. So similar thing applies to satellite image. So when we are talking about classification, we're trying to group similar pixel that have similar reflectance together and categorize them into, let's say, vegetation, built up, roads, and the like. So that's the classification in simple terms. So we are going to use this part to illustrate classification task. So this is a very high resolution image. So we are going to take this portion and we are going to see it in medium resolution, which doesn't appear clearly, but just to understand what we want to do. So here you can see two major features, the built up, very bright, as well as the vegetation cover. Again, just to show us what we want to work on, and in medium resolution. So we want to see how these two features behave in each spectral band and compare it to what we have in this standard curve. So this is a built up roof A, this is a vegetation B, and we're going to be interpreting the appearance in each spectral band one after the other. So we assume that this box is a single pixel of 10-meter resolution for this particular illustration. Sorry. So looking at the blue band, and this is like a practical thing that I did in QGIS. So when you check the pixel value of this particular bit up, so it has a very high reflectance value compared to vegetation B, and this corresponds to what a standard reflectance curve tells us about bit up and vegetation. Like bit up is similar to soil. So you see like bit up has high reflectance in the blue compared to vegetation. So moving forward, if we check the reflectance in the green part, of the spectrum. So as we expected, there is increase in the reflectance of B-top. You see more than 5,000, and increase in the reflectance of the vegetation in the green part, because vegetation reflects most of the green energy and it appears green. So you can see it's increasing like this. So when we go to the red portion, so we expect increase for B-top or soil in the red portion. So it increased, but not very much. But for the vegetation, we expect a decrease in vegetation reflectance, like it has to drop in the red because it absorbed most of the red portion of the energy. So can anyone tell me, like, what would the value of the vegetation look like in the infrared? Is it going to be closer to the value we have in the blue or red, or more than the value that we have in the blue or red? Like, you can check, you can type it in the, just like, is it going to be close to the value we have in the blue and red for the vegetation, like the value of the reflectance in the infrared, or is it going to be more than that? Yeah, thank you. Yeah, thank you so much for the contribution. That's actually correct. So because the infrared, the vegetation has the highest reflectance in the infrared, so we expect a very high value. And as you can see, the value or reflectance value of vegetation in the infrared is even double the reflectance in the green, and it reflects or it emulates what we saw in this particular curve. So this is a way that we can use to show our understanding of like how several features reflect energy from the sun and how it's influenced the way they appear on different parts of the band or channel or spectrum. So now we can transform this information to a curve, just like you can tabulate the reading, plot it in a Microsoft Excel or Google Sheet, and see how it appears. So you can see it actually reflects what we saw before. So you have the blue for vegetation, you have low reflection in the blue, slightly higher in the green, but very high in the infrared. So for the built-up, it's like a very like gently increasing reflectance. So this is like a basic example of how we can interpret reflection for several features across several components of the spectrum. So moving forward to actual classification task, because as human beings, we can't be able to classify a large amount of image with this approach I showed earlier. It's not possible to be looking at each pixel one after the other and be repeating this process. But this is just for us to understand the basic of what the computer actually does. So we have what we call unsupervised classification. So what happens here is that you have an image, you give it to the computer or the classifier, and you give the computer or algorithm the liberty to help you look at the image and group the pixel based on their similarity. You will now define the number of class that you want as an output. Maybe now you give this image to an algorithm, you tell the algorithm to group this pixel in the image to, let's say, 10 classes. So it will now give you the classes. When it gives you the classes, you now interpret the classes to the features that you think they belong to. So that's unsupervised. You don't actually supervise the classification. You give the computer the liberty or the freedom to perform the grouping for you. So in supervised classification, so you, the expert, you define the class for the computer and you tell the computer where these classes are, like this pixel belong to this class. Then use this sample to learn and then classify for the whole pixel. So this, you have a defined number of class, you have a sample that you give to the computer, then it helps you to classify the image by learning from the sample, and it gives you the output. So this is what they call supervised classification. So we also have, from another perspective, we have what they call pixel-based classification. So it's similar to what we did earlier. We look at each pixel one after the other and try to determine, like the machine or the computer look at each pixel one after the other and determine which category or class they belong to. So one issue with this is that, like I showed at the beginning, the issue of missed pixel, because we don't have pure pixel most time. So it can have some missed classification, like it can have some wrong classification because of the pixel issue and some other factors that influences it. So the other approach is the object-based. So here, instead of treating the pixel as single units, so we try to look for a group of similar pixel from the start. So this is as like three broad process. So before we used to look at single pixel, but here we are looking at group of similar pixels. So we now group them together into what we call image, objects, or segments. So you can see here, this looks like vegetation because it's displayed in first color infrared combination. So the red color here are showing vegetation or crops. So it tried to group them based on their similarity. So the yellow boundary are the boundary or the group of the pixel. They are called segments or image objects. So when we zoom in to one of these, so for example, let's zoom into this. So here, it has grouped all the pixels here as a single image object, or what we call segments. So there are a lot of pixels in this single segments. So we have more than 1,500 pixels. And remember, we are dealing with multispectral, like more than one part of the spectra region. So we have several bands. So we have like 8 bands for this particular sensor. We have more than 1,500 pixels for this single segment. So now you now compute some kind of aggregate statistic. So you compute like the mean of the first band for all the pixels here. You compute like the mean of all the pixels for the second band. So you repeat that for all the bands. You also compute some other statistic as you might wish, like the variance, the maximum, and all these kind of statistics. So you now use, instead of classifying single pixel, so you are now classifying the whole group of pixel by using the aggregate statistic of the pixel. So you can see here the result of the classification. It follows the shape of the segment. So this is actually better if you are dealing with features that are very large and maybe like from boundary extraction, like crop fit, boundary extraction, building detection, and maybe crop or tree classification. So this is just like to show the difference between object-based and pixel-based. So you see like some kind of mixed classes in this part. You see like kind of a grouped class, and they have like a kind of defined boundary. So this mixed pixel or mixed classes is what they call salt and pepper effects. So apart from using the spectral band, you could also use some supplementary information that will help you when you are doing satellite image analysis. So you can use like Google-based map to see what kind of features do we actually have here. So also you can use like combination of several bands. You can use spectra indices, which you do like arithmetic operation on several bands of the image. So another thing is that we have centered the talk here on the optical satellite image, but you can also combine several sensors like optical SAR image. You can also extract some feature like texture feature, filter operation and add it to the spectral band. Like instead of using just the visible like blue, green, red, infrared, and the microwave, the thermal for your classification. So you can also add spectra in this layer. You can add texture layer as inputs to classify your image. This will give the model or the computer more information to be able to distinguish the features. So I've talked mainly about land cover, for example, but satellite image analysis goes beyond land cover alone. So here you can see this paper, they try to classify different type of tree species. So they apply segmentation to get the boundary or the grouping of the similar pixels or reflectance. They now apply the classification to distinguish the trees and separate the building from the trees. So another example like the crop classification, which is similar to the example I showed earlier. So you have sample of crop, you want to distinguish them. And this is very like a bit of tricky because they all belong to the class of vegetation, but they appear differently and also they will have different reflectance properties depending on the growing stage and the like. So you need to consider some other kind of information apart from the spectral band in this kind of analysis. So also, this is also like about trying to distinguish weed from the crop. So this is even more technical because weed and crop, they belong to the same class of vegetation. But one important thing that we can learn from this is that the height of the weed and the crop will differ, especially at the start, at the growing stage, at the start of the growing stage of the weed. So what they do is to also apply some additional information like the digital surface model. So digital surface model will ensure or enable the algorithm or the computer to see or learn more about several factors that it could use to distinguish weed from the crop because they all belong to a class of vegetation. But when you give it some additional information, so it can use that to distinguish crop and the weed. So to round it up, so I would like to highlight like these points. So the resolution of image, it depends on like the task you want to perform. So for example, if you want to extract building footprint, so you might need high spatial resolution. If you want to perform, let's say flood mapping, flash flood mapping, so you might need high temporal resolution image. If you want to perform vegetation analysis like crop type classification, so you might need image with high spectra, like high number of bands. So also the method may be object-based, pixel-based, unsupervised. So it depends on several factors like the targets, the image that you have available, and the like. Also, another point is like the knowledge of the feature you are looking for. It helps you to interpret the image. So, like the example I mentioned earlier, somebody from a geologic background will have a better expertise in me identifying minerals potential area or geologic faults compared to somebody with just knowledge of remote sensing. So the quality and size of sample that I use to perform classification, it have effects on the result that you get. We are going to look at this tomorrow. So in object-based, there's what they call segmentation scale. So where you determine the number of pixel that it should group and also like the kind of distance it should look for before you stop grouping the pixel. And like I mentioned, supplementary information are very helpful to interpret an image. So tomorrow we are going to do the practical aspect and also go deeper and focus on land cover classification. So these are some of platform or website that you can learn further about image and remote sensing. And yeah, thank you for joining.
So is this the end for today?
Thank you so much, Lukman, for this great presentation. And if you have any question, you can just put up your hands and I would unmute you for you to ask the ask him if you have any questions. So just put up your hands using the reaction button and then I'd call you, or you can just type your question in the chat and then I'd call on you to, ask your question, please. Oh, yes, a lot of people are asking about the slides, the material. We have the recording of the Zoom meeting, and it would open a survey tomorrow. You drop your email address, I won't be able to share the slide and the recording with you. So this is the QR code to scan. You can connect with him via LinkedIn, Twitter, or other professional platforms. Okay, I see Muse Mohammed, you have the question. Please unmute yourself and go on and ask your question.
Good. Hello.
Yes, we can hear you, Mohammed. Go on, please, with your question.
Uh, Thank you for having me. My name is Mose. I am a water engineer from from Somaliland. I want to ask you two questions.
Please go on, Mohammed.
First question is, as a water engineer, how can we use remote sensing and satellite images to improve water infrastructures and also improve and also prevent floods and monitor the uh, the functionality of water resources. And my second question is, um, how can we access those satellite images? Thank you.
Yeah, thank you, Musa, for the question. So the first one you asked is about how can you use remote sensing and satellite image as as a water engineer to improve flood risk and monitoring of water resources. So number one, like I hope I get your question correct. So the flood risk aspect, so there are several ways that you can use remote sensing to perform flood risk to know like what is the likelihood of flood occurring in an area. So you have several factors that affect floods. So one of them like is the slope, is the amount of rainfall, is the elevation, and some other factors. So this factor can be modeled in form of image. For example, you have like satellite image that collects information about rainfall, like sensor that collects information about rainfall, which are being transmitted in form of raster or image. So you can use this kind of satellite image or data to integrate them together and use approaches like multi-criteria, machine learning, and use it to model risk or vulnerability of areas to flood. Also, you have population layers in raster format, like the word pop data, which you can use to know like which population or which demographic are vulnerable to flood risk. So these are ways which you can use satellite image for flood risk. Also, you can have satellite images when there is flood events, when flood events have happened. So you can use images of several times during the flood events, use maybe machine learning, clustering approach, deep learning, and classify the image into flood and non-flood pixels. So this will enable you to know the extent of damage and the like. So the second question is, okay, still on the first question, how can you use image to monitor water resources? So we have water quality parameters, which you can estimate from multispectral image. For example, the chlorophyll content in the water, the turbidity content. So you have some kind of spectral indices that you can compute from several bands by combining several bands of the image, like combine the infrared, the green, and the blue, and you carry out some mathematical arithmetic and try to use it to estimate the variation in chlorophyll or turbidity in the water. Also, you can collect, in surface water, let's say lake, you have a very large surface water. So it's not possible for you to monitor every point on that water surface. So you can collect some few samples from the water surface. Then you can now use several spectral bands from satellite image and perform classification or regression. Like you use a few samples and the whole surface of the water is being captured by the satellite image. Then use that to train a model and use the image information to generalize the condition of the whole water surface. So the other question is, how can we access the satellite image? So I think I will put that in the slide tomorrow. So there are several platforms, the Copernicus website, the Google Earth Engine Data Catalog, the STAC catalog, and the Google Earth Engine Community Catalog. There are a lot of platforms that you can get all these open source satellite data. Yeah, thank you.
Okay. Thank you so much, Mohammed, for your question, and thank you, Lukman, for responding. Um, we have Chineba Neville. Please, can you unmute yourself and ask your question? And after that, we'll go to Engineer Mayo. So for now, Chineba Neville, please unmute yourself and ask your question.
Okay, thank you very much for this opportunity. In question, I'm an environmentalist and a GIS specialist in total. So I tend to mostly use softwares like I instead use ArcGIS as the software than QGIS as what he used here. So I wanted to ask if by any chance any of these studies that he has carried out or any of this work he has done, which I must say is very remarkable. How is it feasible that we can be able to carry this out in other softwares that are similar to QGIS? I personally use ArcGIS, so I don't know how feasible that is. If this particular things that or this particular if I may say actions that you have carried out there is possible in ArcGIS. I don't know if that is it. I think that's my question. Thank you.
Yeah, thank you so much for the question. That's a very good question. So the point is that is to understand the concept and the basic of the task so that you can have the flexibility of using several software as you may wish. So, and that's the point of we, all the Africa and environmental science, coming up, making like 2-day webinar so that we understand the concept before we now move to apply it in a software. So you can apply several software for this different task. For example, in QGIS, you can do pixel-based machine learning classification, which we are going to do tomorrow. You can also do object-based, and I believe you can use like deep learning plugins, and there is also like segment anything model that you can use in QGIS. So similarly, in ArcGIS Pro, so there are several tools for pixel-based classification. There are several deep learning models, pre-trained models in ArcGIS Pro that you can easily import. You can also train your model in ArcGIS Pro. So I understand like maybe the familiarity with a particular software is an issue, but once you know how to use a GIS software, just like a single one, so and you understand the concept, so it will be easier for you to adopt any other software. So I hope I'm able to answer your question. So in summary, like most of the functions that we need for image analysis tasks are available in both ArcGIS Pro and QGIS.
Okay, thank you very much. Thank you very much.
Thank you, Chinebel, for your question. I can see Muse Mohammed, your hand is still up. I don't know if that's a mistake because I know we responded to you previously, but if you have any questions, just unmute yourself and ask, please. Okay, I think that's all for the. Okay, I have a question. Jonathan, please unmute yourself and ask your question, please. Jonathan,
Okay. Thank you very much, Mr. Lukman, for your presentation. My name is Jonathan. I'm a geologist and also a geospatial analyst. So I want to ask you a question. Can you hear me?
Yes, I
Yes, we
can.
can hear you.
Analyst.
Oh, okay. So I want to ask you a question. I've seen that you really did a very good presentation, but I'm just curious about the software that you said you're going to use, which is the QGIS. So what about handling raster images using raster softwares like AIES, MV? Uh, because most of what I do is to use this remote sensing based softwares to prepare my own just partial analysis before taking it to this QGIS or ArcGIS and then do the vector analysis and do the finished touches. So can QGIS actually do all these band combinations that we use in softwares like MV, like LDAS Imagine, like all this remote sensing based. Can we actually have it done in QGIS? I'm really curious. So it could save time and then, so please just help me with that. Thank you.
Yeah, thank you so much for the question. Yeah, sure. Like we can do similar thing of even although I'm not very familiar with AIES, but I've used ADAS Imagine and Envy in the past. But we can do almost all the tasks in QGIS. Like band combination is like one of the simplest tasks in QGIS. So we can do several raster analysis in QGIS. We can combine bands, we can clip raster, we can extract bands, we can do a lot of raster analysis in QGIS as well. So QGIS is as like powerful as EDAS or as MV or as AIES, and it supports several data formats. So you can analyze vector, raster, LiDAR, point cloud, and all kind of data, even spreadsheet data. So you can use it in QGIS. And you're going to see like some of the example tomorrow.
Fantastic. Thank you very much. I'm really looking forward to it. Thank you.
Okay, Kada Hussein, I see your hand is up. If you can unmute yourself and ask your question, please. Kada Hussein, please unmute yourself and ask your question. Okay, I don't know if he's here. Thank you so much, Lickman, for this wonderful presentation. I really learned a lot. And if you have any question, please try and connect with Lukman on, just scan the QR code and you'll be able to connect with him. If not, we'll see you guys tomorrow for the practical section. Have a good rest of the day.